Good afternoon. Thanks the organizing committee to give me this opportunity to talk about our research. So I will be mainly talking about some issues in analyzing the untargeted LC-MS data, especially the annotation of ammonia adduct. So I will first begin with the LC method we are using. So we are mostly interested in those polar metabolites. So we are using helical method running on water's amide column. We have ammonia acetate, ammonia, and ammonia hydroxide in the LC buffer to reach a pH around 9. We need this pH 9 in order to see compounds like ATP and NADPH. So in helical condition, we start from the high organic and then go to low organic and back to high organic. So under this condition, the lipid and the fatty acid they will erode earlier, and those polar metabolites they will erode later. So with this method, we established an in-house library using about 500 metabolite standard. With this library, when we look at the liver data, we can confirm the identity of about 300 metabolites by looking at their return time and accurate mass compared to the library data. So of course you know that for a typical LC-MS runs, you see a much larger number of LC-MS peaks. So it is an open question as how many of those LC-MS peak features corresponding to metabolites. There are several things make this complicated. First, there are the background peaks from different sources, and then there are peaks from the natural isotopic, and there are those adducts, which I will talk in more detail later. Then there are those fragments generated at the ion source. So they are also called in-source fragments. For example, when we look at the raw data of this fumarate, you can see that there are actually two peaks. The peak in the left is the true fumarate peak. The peak on the right is actually a fragment from another compound called malate with loss of water. So even though we are in general just looking at just MS1 data, actually in this data there is MS2 information inside this. So these are the in-source fragments. The other issue is that there are those additional compounds that generated during the sample storage. For example, the serine can react with formate to generate a new compound called formal serine, and this will complicate this data. So with all these complications, I think the actual number of metabolites is actually not a big number. So now let's focus on this adduct. So to annotate adducts, in general, we are just looking. We are mainly rely on the information from the delta M over Z difference between peak pairs. So for some of the adducts, like sodium adduct and the potassium adduct, they have a unique M mass difference. So their annotation is relatively straightforward. For a mass difference of water, this in general this results from the in-source fermentation with a loss of water because the water adduct is very rare. Then we have this problem of this ammonia. So when you have a mass difference of ammonia, we really cannot tell if it's ammonia adduct or it's from the in-source fermentation with the loss of ammonia, because they will give you a same mass difference of ammonia. Like here, if you look at, I show here 2 examples. They have a mass difference of that ammonia, but we really cannot tell if it's really ammonia adduct or not. So to solve this, we suggest that then there are 2 ways to deal with this problem. The first is that we can do isotopic labeling of samples. This really only works for those microbials, such as E. coli and yeast. So the way we do it with that, we can let these bacteria or yeast grow in 4 different labeling conditions, either unlabeled or 13C labeled or 15N labeled, or both 13C and 15N labeled. So we have 4 sets of data under different labeling conditions. Then we use a computer program to try to find out the best carbon and nitrogen combinations by going through all the possible combinations of carbon and nitrogen and find that number that give you the best intensity match. So here is an example. We are looking at mass at 505.9. There are multiple possible combinations of carbon and nitrogen. Can be either C10N5 or C11N4, but when we look at the intensity pattern between unlabeled and labeled samples, it looks to us that this combination of C10 and N5 give you the best intensity match, give you a high score. So this was chosen as the carbon and nitrogen number for this peak. So by doing this, for every peak in the unlabeled samples, we can assign them carbon and nitrogen counts. So by doing this, there is one important feature that we can see, that is that all the adducts from the same metabolite, they should share the same carbon and nitrogen count. The reason is that these ammonia, sodium, they come from the LC mobile phase, so they are not going to affect the labeling pattern. So the result is that all the adducts from the same metabolite, they should share the same carbon and nitrogen counts. So in this case, we can confirm that this peak at 625 is ammonia adduct of this peak at 608. The other way is to do isotopic labeling of the LC buffer. This works well for those samples that cannot get isotopic labeled. So we can add some 15N ammonia in the LC buffer. Then when we look at the data with this new buffer, you should see a peak that coming from this 15N ammonia. This confirms that this peak is actually ammonia adduct. So I can show you another example. Here we are looking at 2 peaks at 188 and 205. So by doing the labeling of the samples, we notice that these 2 peaks have different carbon and nitrogen counts. This confirms that this peak at 205 is not the ammonia adduct of this peak at 188, because they have different carbon and nitrogen counts. In fact, this peak at 188 is a fragment from this peak at 205. So using labeling of the LC buffer, we can see that with this new buffer, we don't see a 15N peak. So this confirms that this peak at 205 is not the ammonia adduct of this peak at 188. So using these 2 approaches, we can both reach the same conclusion. So most of the information I presented today are covered under in two recent papers on analytical chemistry. We do have another paper coming out soon, which provide a general tool to annotate the untargeted LC-HRMS data, and I hope you can give it a try. With that, I want to thank Josh and all the team members, especially Lin Wang, Xi Xing, Li Chen, and also thanks the financial support from NIH. Thank you.